We continue our study of quadratic functions by looking at maximums and minimums of quadratic functions. So let's take a look. F of x equals ax squared plus bx plus c, that's quadratic function. The way we know that's a quadratic function is for the same way we know a quadratic equation is a quadratic equation. We have a highest exponent of 2 here. And no denominator, no variables in the denominators or anything like that. If a is greater than 0, then f has a what? Well, let's think about this. If a is greater than 0, that means that this parabola opens up. And if the parabola opens up, it's going to have a picture like this. At that vertex, which is that x equals negative b over 2a is the vertex, remember, you have a minimum of the function there. If a is less than 0, that means it opens down like this, and at that vertex you have a maximum. One thing we didn't really talk about up above was domain and range. So let's just go back here for a second. In this picture, for example, we had a function whose vertex was 1, -1. The domain of all quadratic functions is all real numbers. There are no restrictions on what you can plug in for x. However, the range, this if you wanted it in interval notation, by the way, is -∞ to infinity. The range is what y values do we get? Well, if the vertex is at 1, -1, you get all values of y greater than or equal to -1. We have -1 to infinity, including the -1 on that guy. So that's how we find domain and range. It really depends on what the vertex is. We're going to use this idea of domain and range, minimum, maximum stuff to answer this question down here at the bottom. We have this function 2x squared plus 9x plus 2. Determine if the function has a minimum or a maximum and find that value. The first thing I notice here is that a equals 2 being a positive number means this parabola opens up. And if it opens up, you're going to have a minimum value there. So this parabola, f of x, has a minimum. Let's see where that minimum is. The x value, which remember when we talk about the vertex of a parabola, we usually refer to the x coordinate of the vertex as h is equal to -b over 2a. So -9 over 2 times 2, or -9/4. So the ordered pair has x coordinate of 9/4. And to find the y, which remember we typically refer to as k, that will be f of -9/4. Anytime we're looking for a y value that goes with a particular x value, we plug that x value into the function. 2 times -9/4 squared plus 9 times -9/4 plus 2. 2 times 81 over 16. Oops, that's going to be minus 81 over 4. Plus 2. Let's see here. I'm going to simplify the 2 and the 16 to give me 81 over 8 minus 81 over 4 plus I'm going to write that with denominator 8. So we have 16 over 8. Multiply this by 2, I would get 162 over 8. So when I subtract that, I get negative 81 plus 16 would be negative 65 over 8. That's a nice round number. When I get weird numbers like that, I know that it's possible, and that's okay, but I do want to check to see if that really is correct. So I'm going to go to my graphing calculator. I'm going to show you how to do that on the TI-84. For those of you that are using Alex, you do not need a graphing calculator necessarily because there is one there. But sometimes it only pops up when it thinks you should use it. And so it depends on the question if that really is going to be available to you. So we're going to graph this in the calculator. Y equals, I put this function in already, this 2x squared plus 9x plus 2. We saw in a previous couple of videos how to put that in, so if you're not clear about that, you may need to go back and review those videos where we did that. Or find some YouTube videos too if that's helpful. So we put the y equals in. I'm going to go ahead and graph this. This is our parabola. We're in the standard window here, I think. Let me look here. Yep, negative 10 to 10, negative 10 to 10 on our x min and x max, y min and y max. What I want to know is where that vertex is. To find that exact point, the best bet is to go to this calc menu, calculation. So we do second, and the trace button takes us into that calculate menu. And if you notice here, 3 and 4 give you minimum and maximum. This particular one is a minimum because it opens up. So we're going to hit minimum. Then it asks you for a left bound. So I'm just going to move my cursor over so that it's on the left side of that vertex. And then hit enter. And then it asks for a right bound. So you put your cursor over on the right side. And then a guess. And the more accurate you are with these, the quicker it'll be. So that's why we're doing that. So we're going to guess right around there. All right, it tells you the minimum is negative 2.25, negative 8.125. Now that's giving you decimals here, and these kind of seem like they might be exact values, but sometimes this is going to give you an approximation. For example, if your fraction is 1/12, well, that's going to give you, if your x value was 1/12, that's going to give you the decimal approximation of that. Let's go back over to our notes and see if these numbers are equal to what we got. Negative 2.25, oh, yep, 9, negative 9 over 4 is the same thing as negative 2 1/4, or 2.25. Negative 65 over 8 would be negative 8 1/8. Well, 1/8 is that 0.125. So we do have the right numbers here, despite their ugliness. We have 2 more questions here. Domain. Here's one of our answers to our questions. I'm just trying to, we've got a lot of stuff written here, so I'm trying to clarify here. The domain of this is all real numbers. There are no restrictions on what I can plug in for x there. The range, let's think about our picture. We have a minimum, negative 9 1/4. I'm sorry, negative 9/4, negative 65 over 8 is here. And remember, it opens up. So whatever it looks like. I'm just sort of in a rough sketch here because it doesn't really matter. What matters is that negative 65 over 8 is the smallest y value. So y has to be greater than or equal to that number. In interval notation, it would be 65 over 8 to infinity, bracket on the 65 over 8. We always use a parentheses on infinity or negative infinity. So that's our range. By the way, if you're looking for interval notation for all real numbers, negative infinity to infinity. Okay, let's look at a couple applications of this. Why would we care about that minimum or maximum value? Here we have a small rocket launched from the ground. The height h in feet of the rocket t seconds after it is launched is given by h of t equals negative 16t squared plus 128t. What is the greatest height the rocket achieves? Well, for one thing, let's think about what's happening here. It's launched from the ground, goes up, and has to come back down. So it is going to achieve a maximum there just based on what we know about physics in our world, right? What we have observed. But we also know that this is going to have a maximum because of that negative coefficient on the t squared. Let's go ahead and find that. That's really what this is asking you to do. Find the max height. Let's start with t is our independent variable here instead of x. Negative b over 2a. That will be negative 128 over 2 times negative 16. Negative 128 over negative 32 is 4. That is the t value. T is our independent variable here, t for time. H of 4 is negative 16 times 4 squared plus 128 times 4. That is going to be what? Negative 256 plus 512. So we get 256 here. I'm just going to double check my numbers just to make sure. 128 times 4. Yeah, that is 512. Okay, very good. That means our vertex is at 256. We found the vertex, but that doesn't mean we understand what it really means. Remember, the independent variable here is time, and the dependent variable here is height. After 4 seconds, the height of the rocket is 256 feet. And because that is the vertex, we know that is the maximum height. The picture here is this, right? Where this peak is at 256. It says it's launched from the ground. Let's answer the questions here. Part A, what is the greatest height the rocket achieves? That's that 256 feet. Part B, how long did it take to get there? 4 seconds. Part C, how long is the rocket in the air total? There's 2 approaches to this. We want to know how long did it take to travel this whole path, right? So back to here. Because of the symmetry of parabolas, we know if it takes 4 seconds to reach that peak, it's going to take an additional 4 seconds to come back down to the ground. So the answer here has to be 8 seconds. That only works here because it was launched from the ground and went back to the ground. These 2 points, a different color here. These 2 points are symmetric on the parabola because they're both at the ground. If they're not, like say for example, you're looking at a baseball that was hit from 3 feet off the ground and you want to know where it hits the ground, those aren't symmetric because you started at 3 feet off the ground versus hitting the ground. So be super careful here. One way to make sure that you're avoiding this trap is to just say, how long is the rocket in the air? That means you want to find t when h is 0, right? How long till it gets back to the ground? So we're going to set that function equal to 0. Negative 16t squared plus 128t. Easiest way to solve that is to factor out the negative 16t. And when you take the negative out, that leaves t minus 8 there. Set the factors equal to 0. We're solving a quadratic equation here, right? It happened to factor. This one gives t equals 0. That's where it started on the ground of height 0. And t equals 8 seconds. That gives us this. So just be really super careful. It depends on how this question is worded. All right, is the rocket traveling faster from 0 to 1 seconds or from 3 to 4 seconds? Well, first I'd ask what makes sense to you. What makes sense? Do you think it's traveling faster from 0 to 1? So from this first red point to maybe this point here? Or is it traveling faster from this point here, green, to this vertex up here? Intuitively, to me, it's probably traveling faster from 0 to 1 second. But we should probably do some work here to justify that. I am going to find the average rate of change of this rocket over that time. Average rate of change. So I am going to do h of 1 minus h of 0 over 1 minus 0. And I'm going to do h of 4 minus h of 3 over 4 minus 3. H of 1, let's go back here. So we're just calculating the slope connecting these 2 points, right? The average rate of change. How much did it change in that 1 second interval? Well, let's go back up to this function. When t is 1, I have negative 16 plus 128. So that's going to be 112. That 112 just comes from plugging 1 into the function. H of 0 is 0 and 1. So I have 112. Is that feet? Yeah, we're in feet here, right? Feet per second. Let's do this guy. I know I'm cramming this in here a little bit. Sorry about that. H of 4. Let me show you a kind of cool way on the calculator to find this. While we're here, I may as well show it to you. We can plug that 4 in, right? Or we can allow a calculator to find it for us. We already have the function in, oh no, this is a different function. What is our function? Negative 16. I'm going to use, let me clear that out. Negative 16, I'm just going to use x. It's just a variable, right? It doesn't matter what letter you use. You could use a smiley face. Plus 128. is our function. Let's go ahead and graph that. Whoa. Oh yeah, it goes super high, right? That's why we're not seeing, that's the parabola going up. Goes up to 256, right? So if I wanted to see it, I need to make my Y window go up to 256, so maybe 260. And I don't want to go by ones. If I'm going that big, I would go maybe by 20s. I don't need all these negative x's. Remember that we're talking about time here. So maybe -1, oopsie, -1 to give us a little bit of space there. Okay, sorry about my dog. Okay, so now we can see our parabola here. What we wanted to do here was find the values of this function at x equals 4, which we already actually know that one. That was that vertex. It was 256, right? When we plugged in 4 into the function, we got 256. So I can go ahead and put that one here. 256 minus. Now we need to find h of 3. We could do the same thing we did up here and throw that 3 in. I kind of wanted to show you how you can do this on the calculator. The table feature is pretty nice if you do second and table. See how here we have the x's 0, 1, 2, 3, and so on. The y value in the second column there tells us when x is 3, what is y? So in this case, when t is 3, what is h? And the answer is 240. So let's put that in. That's my h of 3. 240 over 1. So you get 16, cramming this in here, 16 feet in that 1 second, right? To answer this question, is the rocket traveling faster from 0 to 1 second or from 3 to 4 seconds? Well, the average over that 0 to 1 time interval is 112 feet per second compared to the average over the 3 to 4 second is only 16 feet per second. So our answer here would be it travels faster from 0 to 1 second. I'm sorry you have to cram all that in there. I did not leave enough space for you to work on that problem, did I? One thing I did want to show you, what if you don't have, so when I pulled up this table, mine was all nice and pretty, 0, 1, 2, 3, and so on. Yours may not look like that, depending upon how you have things set. You want to go to these table settings, second and window. Above that in blue, it says TBL set, table set or settings, setup. We're going to go there. My table start is set to 0, and my delta table is 1. That means it starts at 0 and it changes by 1. So it goes 0, then it goes to 1, then it goes to 2, and so on. You can also change this. Instead of being auto, you can change it to ask. And then when you go back into the table, you can type in what you want. For x, if we wanted to know 3, which we did, that's at 240. 4, we wanted to know that one, that's the 256, which we had already calculated. So there's some nice features in there. This is also available in the Alex calculator. So just kind of play around with that if you want when you get into those problems. Okay, that's our rocket problem. Let's do one more maximum and minimum problem here. We have a farmer with 160 feet of fencing to enclose 2 adjacent rectangular pens. What dimensions should be used so that the enclosed area will be a maximum? Two adjacent rectangular pens. So adjacent means next to each other. I'm going to draw a picture here. It actually doesn't say that they're the same size, so you don't make that assumption. So don't make that assumption, okay? We want to know what dimensions should be used so that the enclosed area will be a maximum. Let's call this one X. That makes this X and this X, right? Because we don't know where this fence is, because it doesn't say they're two rectangular pens are the same size. It could be way over here, right? We're not going to make any assumptions there. We're just going to call this whole dimension Y. That makes this whole thing Y. All the way to the edge here. Okay? What dimensions should be used so that the enclosed area will be a maximum? I always try to ask myself on these problems, what is my goal? In this case, my goal is to maximize area. You have to know what you want to do, right? If I want to maximize area, I have to know a formula for area. In this case, this middle dimension here, get rid of this. This middle guy has no impact on the area at all. This area is just X times Y. The length times the width. The problem here is we have three unknowns. We have area, we have X, and we have Y. X and Y would be like two independent variables where area would depend on what those are. We'd like to get that to be a function of one variable instead of two. So we need to think about what other information we have that we haven't used. The answer to that is this 160 feet of fencing. We have 160 feet of fencing to enclose these pens. That 160 has to cover 3 X's and 2 Y's, right? It has to cover this, which is X, this, which is X, this, which is X. So there's 3 X's, and then you got a Y here and a Y here that all have to be fence. So 160 equals 3X plus 2Y is kind of a perimeter question there. Let's take that equation and solve it for Y. I'm going to show you Y in a second. Let's divide both sides by 2, and I get Y equals 80 minus 3/2 X. I can then take that equation and substitute it in here so that I have area as just a function of X. This is not A times X, but just function notation. Area as a function of just X when I replace Y with 80 minus 3/2 X. I'm going to go ahead and distribute that. I have my area, A of X, is 80X minus 3/2 X. It might help you to see this in descending order, putting that highest exponent first, to recognize that this is quadratic. And if it's quadratic, it's a parabola. And if it's a parabola, it has a minimum or a maximum at the vertex. This particular one opens down because of the negative 3/2, So it has a max, which is what we were hoping for, right? We want to maximize the area. So let's find that. Find the vertex, because that's where the max will be. Let's find the x. It was, remember, negative b over 2a. So negative 80 over 2 times negative 3/2. Negative 80 over 3, negative 3. So 80 over 3. Or let's see, if we divide that, what do we get? 5 would be 25, 78 would be 26 and 2/3. Okay, now what does the question actually ask for? It asks for what dimensions. I don't even need to find the area. I don't need to plug that x in, because when I plug the x in to this equation, it is going to give me the area. I don't need that. All I need is the dimensions. I have this, the vertical dimensions here, the x, to be 26 2/3 feet. I need the y. I am going to use this equation to find the y. Y equals 80 minus 3/2 times, I'm going to write that as the 80 over 3. I think it's easier to multiply as a that improper fraction. The 3's simplify. Let's do this here. 3's simplify, and that gives me 80 over 2, which is 40. So I have 80 minus 40, or 40. So let's come up to this space. My pen should be 26 2/3 feet by 40 feet. That will give me a maximum area, because that is where that x value is where the vertex of the parabola is. So that has to be the max of it. Cool, I like it. We already talked about finding the maximum or minimum on the calculator. I just wanted to make sure we addressed that. So that's why I kind of put a little reminder to myself here to make sure we did that. Parabolas show up in a lot of physical applications. We saw the idea of the rocket ship and the path it, the function of time compared to its height. Here we see it. We saw the picture of the ball and the diver and those kind of things. So a lot of physical things follow a parabolic path. So I want to emphasize to you how important this concept of quadratic functions is. So make sure you study these up really well.